Good morning. So this is the next video related to liquid additive manufacturing. So we learned about the basics of 3D printing technology, such as the basic definition of 3D printing, its material capabilities, geometric capabilities, then the different types of files we are using, how we will prepare the solid model with the help of CSG approach, boundary representation or feature-based modeling. Then we will cover then we have covered the slicing, the STL file format, etc. So we have covered the basics of 3D printing technology. Based on the raw material we are using, the classification is we can classify 3D printing technology as liquid raw material 3D printing, solid raw material 3D printing. Till now, gas raw material is not using to prepare the solid. Liquid raw material and solid raw materials are using to prepare the solid model with the help of 3D printing technology. So the first one, that is liquid additive manufacturing, whereas we are using the liquid as the raw material. That's why this technique is called a liquid additive manufacturing technology. The raw material we are using is liquid. Here in this figure, this is an example. This is actually what photopolymerization. This is called what photopolymerization. Here, this tank is called what. This is called what. Here you can see this is called what, and inside this tank, this is the liquid. This is the raw material we are using. This is in the liquid format, and this is liquid photopolymer. And we will convert this liquid into, this is our object, this is our solid model. From liquid we will convert this into solid model. So this is what photopolymerization. Clear about this. Yeah. Okay, so let's start. Photopolymerization and rapid freezing. There are two distinct methods used in liquid additive manufacturing. Photopolymerization involves using light to cure layers of liquid resin, while rapid freezing entails using a cold temperature to solidify the liquid material. So here in the case of liquid additive manufacturing, the raw material we are using is liquid. We will convert this liquid into solid form. So with the help of two distinct methods, that is one is photopolymerization and rapid freezing. These techniques offer unique advantages and are applied in various industries for creating intricate and precise 3D objects. As per the ASTM classification, the two methods that are using liquid as the raw material are one is watt photopolymerization. This is the watt photopolymerization, and the second one is material jetting. So the basic difference between material jetting and watt photopolymerization is, here in this material jetting, the material is like a jet, and it will reach the platform or it will reach the substrate. While traveling from this extruder to the substrate, it will interact with the curing lights. So these are the curing lights, and this liquid will convert into solid form. So this is the process involved in material jetting. And in the case of watt photopolymerization, here the liquid raw material, that is photopolymer resin, is inside a tank. This is called a watt, and with the help of a laser, with curing properly with the help of a laser beam, we will convert this liquid into solid form. So these are the two classifications as per the ASTM, American Society for Testing and Materials. So these two techniques are using liquid as the raw material, that is watt photopolymerization and material jetting. In watt photopolymerization and material jetting, the process involves using raw materials in the form of liquid resin. These liquid resins are used as the base material for creating 3D printed objects. The liquid resin is selectively solidified or cured by light or heat to build the desired object layer by layer. This method allows for the creation of intricate and complex geometries in the final 3D printed parts. Then what is the basic difference between photopolymerization and rapid freezing? In the realm of additive manufacturing, two methods that involve the use of liquid raw material are photopolymerization and rapid freezing. Photopolymerization utilizes a process where light causes liquid resin to harden and form the desired shape, while rapid freezing involves the controlled freezing of a liquid material to create a solid object layer by layer. Both methods offer unique advantages and applications within the additive manufacturing industry. Coming to the photopolymerization based liquid additive manufacturing, in the figure, you can see three different stages. The first one is the initial stage, second one is the first curing stage, and the last one is the second curing stage. So photopolymerization is a key process used in 3D printing and various other applications. It involves the UV light, the use of UV light to initiate the curing of photosensitive resin. In the initial stage, you can see UV light turns off, and in the first curing stage and the second curing stage, UV light on. When the UV light interacts with the resin, so this is the resin, this is the photopolymer liquid resin. When the UV light interacts with the resin, a photochemical reaction takes place, leading to the transformation of the resin from a liquid state to the solid state. So when the UV light is in contact with the photopolymer liquid resin, the liquid will convert into solid state. This conversion is essential for building solid three-dimensional objects by gradually adding layers of the liquid resin. The photocurable resin is composed of two primary components, the photoinitiator and the monomer. In the visual representation, the black color is used to depict the photoinitiator and the other represents the monomer. The photoinitiator plays a crucial role by absorbing energy from the UV light and generating free radicals. Once the UV light is in interact with the photoinitiator, it will absorb the energy and it will generate free radicals. Subsequently, the photoinitiator along with the free radicals initiates the transfer of these radicals to the monomer, leading to the formation of chemical bonds. This intricate process is fundamental to the solidification and layer by layer construction of the 3D objects. As I already mentioned, the liquid resin is in contact with the UV light. So we must know about more details about UV light or UV rays. So what is UV energy or UV light or UV rays? UV means ultraviolet. So ultraviolet light is a type of electromagnetic spectrum, electromagnetic radiation that falls within the wavelength range of 100 nanometer to 400 nanometer. So in the figure, it is clear that the wavelength falls within the wavelength range of 100 to 400 nanometer. This places it in the spectrum between the visible, this is the visible light, and X-rays. So this is the UV spectrum. UV light is invisible to the human eye, but its effects are widely observed in everyday life, such as in the way it causes sunburn and fades colors. UV light is further categorized into UVA. Here in the figure you can see UVA, UVB, UVC, each with different effects and applications. Then, what are the, I will clear, yeah. Yeah. What are the subsystems involved in additive manufacturing? The number one is called a photopolymer liquid. Photopolymer liquid. Here in this figure, you can see this is the photopolymer liquid. Then the UV light. The second subsystem is the UV light. Then the scanning system. Properly scan each and every layer. Then the build direction. Okay. Build direction means is it plus Z or minus Z? Build direction. Then the recoating system. So these are the different subsystems involved in liquid additive manufacturing. So once again, in photopolymerization 3D printing, the system comprises several key subsystems. These include the photopolymer liquid, which serves as the material for creating the 3D objects, and the UV light, which initiates the photopolymerization process. The scanning system is responsible for directing the UV light to specific areas, allowing for precise and accurate printing. Additionally, the build direction system determines the orientation of the printed object, while the recoating system ensures even distribution of the photopolymer liquid for each layer. Then next is the different types of scanning system. So we already mentioned what are the different types of subsystems used in liquid additive manufacturing, such as photopolymer liquid, UV light, scanning system, build direction, and recoating system. Again, there are different types of scanning system used in liquid additive manufacturing. Yeah. So what are the different types of scanning system? Scanning system types. Scanning system types. Number one, first one is the galvanometer system. Number one is the galvanometer system. The watt photopolymerization process utilizes various scanning systems, including galvanometer. Then second one is flying liquid. Then third one is flying optics. Then DLP, digital light processing. DLP, digital light processing. In the case of galvanometer system, here from this figure, you can see the galvanometer system involves the arrangement of two mirrors orthogonal to each other. Here you can see X mirror and Y mirror. These mirrors play a crucial role in accurately adjusting the laser beam within the photopolymer liquid resin. The advantage of utilizing mirrors in the system lies is their small mass, enabling rapid deflection at very high speeds. Furthermore, the incorporation of an F theta lens serves to correct any beam errors that may occur during the scanning process, ensuring precise and accurate results. This lens plays a critical role in maintaining the integrity of the laser beam and compensating for any deviations that may arise. The second classification is called a flying liquid. The process of watt photopolymerization involves the use of different scanning systems such as galvanometer, flying liquid, flying optics, DLP. In the case of flying liquid system, the laser source, I will show you another picture. Yeah, here in the case of flying liquid system, the laser source, this is the laser source, this is stationary. The laser source is stationary, remains stationary, while the liquid bud, this liquid bud moving, the liquid bud moving along the X and Y directions. This movement allows for precise and controlled exposure of the liquid resin to the laser, facilitating the solidification of the material in a layer by layer manner. This technique is commonly used in additive manufacturing process, enabling the creation of complex and intricate 3D structures with high precision and accuracy. Then the next scanning system is called flying optics. So flying optics means the laser or UV light is this is moving. The laser or UV light is dynamically moving during the printing process. Okay, so that is the difference between flying liquid and flying optics. Then next is the DLP, digital light processing. Where is the DLP? Okay, no problem. Where is that DLP? Okay, I will search DLP, digital light. Yeah, DLP. Yeah. So in this image, you can see the DLP, digital light processing. I will show another figure. Yeah, you can see. So this is the UV lighting. Okay, so the watt photopolymerization process relies on the integration of multiple advanced scanning systems, each with its unique functionalities. These systems encompass galvanometer, flying liquid, flying optics, DLP, etc. DLP consisting of entails an array of mirrors and is a prevalent technology in modern projectors. In this DLP, you can see this consisting of a projector cast light over the entire layer to cure it cure it all at once. In the case of laser beam, laser beam selectively cures the liquid resin spot by spot. But in the case of DLP, a projector cast layer a light over the entire layer to cure it at all once. So that is the basic difference between a laser beam and a DLP based system. Then next is the shape of the liquid we are using. Before that, shape of UV light. Yeah, in the context of shape of UV light used in watt photopolymerization, it's worth noting that UV light can be employed in the form of a laser beam or as a floodlight. Either in the form of a laser beam or floodlight. Floodlight, as the name suggests, covers the entire area. It will cover an entire area like this. See this image. Floodlight, as the name suggests, covers the entire area, providing light uniformly across the surface. On the other hand, a laser beam is characterized by its ability to concentrate light at a specific spot. The laser beam will concentrate light at a specific particular spot, ensuring precision and accuracy in the photopolymerization process. While floodlight is readily available across the area, the laser beam is confined to a specific location, allowing for targeted application and control. Then, next is the shape of the liquid we are using. In the realm of liquid additive manufacturing, two primary forms of liquid are utilized. Liquid vat, so this is liquid vat, and liquid jet. Liquid vat involves the use of a tank to house the liquid resin, while liquid jet refers to the process of injecting the material into the substrate. This process is specifically known as material jetting. Here in vat photopolymerization, we are using a tank to house the liquid resin. But in the case of material jetting, like this, here, this figure is representing material jetting. Here, this is the material, and this is the resin tank. So from this resin tank, material is coming. Liquid jet refers to the process of injecting the material into the substrate. So here from the extruder, the material is injecting from the extruder to the substrate. This is what is called a material jetting. This process is called a material jetting. So these are the shapes of liquid we are using in liquid additive manufacturing. Then what about the build direction? Yeah. So what about the build direction? In the context of liquid additive manufacturing, the process involves three primary building directions. One is plus Z, then minus Z, then variable direction. The variable direction is particularly intriguing as it entails the ability to integrate the laser with a robotic arm. Here we are using a robotic arm. Here laser is connecting. And when the robotic arm is moving like this is what is called a variable direction. The ability to integrate the laser with a robotic arm, enabling the arm to maneuver in diverse and adaptable trajectories, thereby enhancing the flexibility and precision of the manufacturing process. The other two building directions are plus Z and minus Z. So plus Z means, so this is the platform, and we are building like this above the platform. Okay, so this is called a plus Z direction. If the platform is here and we are building like this is what is called a minus Z direction. And the last one is the variable direction. Okay, so next is the recoating system. In liquid additive manufacturing, there are three different types of recoating systems: deep dipping, top feeding, and bottom feeding. Deep dipping involves submerging the part into the tank, while top feeding utilizes a hopper to feed material from the top side. Bottom feed recoater system is used when the part is built in the minus Z direction, where the liquid is fed from the bottom side under gravity, requiring no additional feeding system. Then we will explain one 3D printer. That the name of that 3D printer is SLA 750. Yeah, this is a 3D printer from 3D Systems, and the name of the 3D printer is SLA 750. First, I will play the video about SLA 750. Yes, that's about the 3D Systems SLA. So the name of the 3D printer is SLA 750. The SLA 750 solution offers a significant advancement in additive manufacturing, productivity, speed, reliability, and automation. It includes the SLA 750 family of large format 3D printing systems, advanced production grade photopolymer materials, the post-cure 1050 post-processing system, and the Octon cloud-based manufacturing operation system. The solution enables the high-speed production of large parts. From the original inventor of SLA and the innovation leader in production-grade photopolymer technology, 3D Systems introduces the industry's fastest SLA 3D printers, the SLA 750 and the SLA 750 Dual. The SLA 750 Dual is the world's first synchronous dual laser SLA printer, delivering up to twice the speed and triple the throughput of current SLA printers. It uses dual imaging system along with a proprietary scan algorithm, hyperscan vector technology, developed especially for efficient high quality production manufacture. The single laser SLA 750 can be upgraded to the dual laser SLA 750 Dual, which allows you to increase productivity in response to growing demand. The SLA 750 and SLA 750 Dual 3D printers use a proprietary scanning algorithm designed specifically for production additive manufacturing. Unlike traditional SLA 3D printers that use of the shelf scanning technology, the hyperscan vector technology optimizes speed and productivity to meet the demands of high volume applications and manufacturing environments. The SLA 750 and SLA 750 Dual are equipped with downstream automation readiness and robot compatibility for 24/7 lights out operation. This includes fully automatic printer turnover with a job offloading, washing, and onboarding. Both 3D printers come with a robot accessible chamber handle, fixed start and stop buttons, robot cycle starts controls similar to existing CNC machines, and automatic bottle or bulk material feed and connectivity ports. Post-Cure 1050 is an industrial scale post-processing system that offers up to 10 times higher throughput compared to similar systems. It provides high volume, high-speed drying and curing for batch jobs and large parts measuring up to 1050 by 750 by 600 mm. The system features optimized light wavelength, separately configurable configurable UV intensity, and actively cooled LEDs with a separately adjustable heating to ensure optimal part curing without causing unwanted thermally induced warp in your printed parts. It also offers factory floor integration, management, and control. The SLA 750 uses Octan's best-in-class cloud-based AI-powered manufacturing operating system. This OS unifies engineering and production through IoT and machine learning to solve manufacturing challenges across industries. Octan's manufacturing OS seamlessly integrates additive manufacturing with your factory floor equipment. It allows you to schedule your production and post-production processes for efficient machine utilization. Additionally, it enables you to connect machines to achieve full traceability and gain valuable data insights. This is end-to-end file to print software. The SLA 750 uses 3D Sprint, an advanced single interface software for file preparation, editing, and printing and management. It allows you to quickly and efficiently go from design to high quality, true to CAD parts without needing additional third-party software. 3D Sprint is optimized for production environments, offering the latest time-saving workflows, UI and UX to maximize printer capacity and build volume utilization for batch run jobs. It sets a new standard for SLA production throughput, quality, and capability. The SLA 750 provides exceptional surface quality and accuracy for large builds, offering superior detail resolution, smooth wall finishes, and precise fidelity. It utilizes production-grade photopolymer materials, advanced software workflow, and optimized laser scanning technology to deliver a high-throughput, automation-capable solution for production SLA. Applications include manufacturing aids, jigs, fixtures, end-use production parts, mass customization, under the hood components, wind tunnel test models, investment casting patterns, mandrel tooling, molds, dies, medical and biocompatible parts, cast urethane, vacuum casting patterns, and high clarity transparent products and components. So that's all about the basic idea about liquid additive manufacturing. So we learned about the basic concepts of liquid additive manufacturing, the two classifications such as photopolymerization and the rapid freezing. So we covered the concept of what photopolymerization and the different subsystems used in what photopolymerization, then the different types of scanning systems used in what photopolymerization, and finally we saw a stereolithographic 3D printer such as SLA 750. The 3D printer is from the company named 3D Systems. Thank you.